Okay, so in the last section of this chapter, I want to talk about the EEPROM in AVR. So every member of the AVR microcontrollers has some amount of on-chip EEPROM in there. And the Atmega 128 has got 4096 bytes of EEPROM. This is because the data in SRAM will be lost when the power is off, and however, we need a place to save out data to protect them against the power failures. So in order to do that, we can use an EEPROM memory. In the EEPROM, we have got three registers dedicated for, in the AVR, we have got three registers dedicated for EEPROM. The first one is EEARH, EEARL. Now, these are address register high and low. So, address register, that represents high, and that represents low. These two together, they actually make a 16-bit register. That's why we have got low byte and the high byte. In order to address each location in the EEPROM memory space. And when you want to read from or write to the EEPROM, you should load EEPROM location address in these EEAR registers. And the important thing about these EEAR registers, the 12 bits of the EEAR registers are used for Atmega 128. So only 12 bits used for Atmega 128. So this is actually giving us 4096 byte EEPROM locations. Okay, another important register in EEPROM, or AVR for EEPROM, it's EEDR. EEDR is actually EEPROM data register. Now, EEPROM data register, in order to write to an EEPROM, you have to write it to the EEDR register and then transfer it to the EEPROM. Or also, if you want to read from EEPROM, you have to read from EEDR. And it's like a EEDR is a bridge between the EEPROM and the CPU. And another register is EECR, which I'm going to talk about that in a little later, because there are some important things about it. This is the EEPROM control register. So we have to know how to configure EEPROM, and this has to be done using the EEPROM control register. So this is actually telling the AVR or the EEPROM to select what kind of operation to perform and so on. And can be the operations can be like the start, read, and write operations. I'm going to talk about that later on as well. Okay, so EEPROM address register, EARH and EARL. As you can see, for Atmega 128, as I already mentioned, we are using 12 bits of it. So most significant 4 bits are unused. Okay, so these are used to specify the location of the EEPROM memory that you want to write or read to. Then the data register, as I already said, is a bridge between the AVR and the EEPROM, because you have to put the data onto ADR, EEDR to write it to the EEPROM, or if you want to read the data, EEPROM has to place it on the EEDR, then the AVR can read it. Okay, so it's in between of those. And the EEPROM control register, we have got set of bits over there that they need to be configured, like EERE and EMWE, WE only itself, and the EERE. Now, these are all configured in the EECR register. Now, EERI is a ready interrupt, so if you want to create an interrupt, you have to enable this one. And whenever the EEPROM completes the operation, it raises an interrupt flag. Now, master write enable. So when it is set, the setting of the write enable within the 4 clock cycle, it starts the write operation. So first, you have to set the master write, and then in the 4 cycles, you have to set the write enable bit. Otherwise, if you don't set this one, if this is 0, even if you set that one, it's not going to perform the write operation. So this is important. And the EERE is the read enable. So if this is 0, then it will cause if the write enable is 0 and this one is set, you're actually reading it. Okay. So when read operation starts, 1 byte from the EEPROM will be read into the EEDR. So once again, when you set the master write to 1, the hardware clears the bit to 0 after 4 clock cycle, and this prevents unwanted write operations on EEPROM contents. So you cannot start read or write operations before the last write operation is finished. So this is AVR is taking care of it. And you can check this by polling the write enable bit. So you can check it if its write is completed or not. So if write enable is 0, it means EEPROM is ready for the next write operation. Okay, so there are a few steps in order to complete read operation and the write operation, which I want to write them over here. EEPROM read. Now, to perform EEPROM read, first of all, we have to wait until EEPROM write enable becomes 0. And then in the second step, we have to write new EEPROM address to EAR. And then the third one, we have to set EEPROM read enable to 1. And the last step is read EEPROM data from EEDR. So that's what we need to do in order to perform read operation. I'm going to solve an example in a minute, but let's see the write instructions as well, or the steps. So EEPROM write, we have to first, again, wait until EEPROM write enable is equals 0. Then write new EEPROM address to EEAR. And then the third step, write new EEPROM data to data register. and then set EEPROM master write enable to 1. And step 5, within 4 clock cycles after setting EEE master write enable, set EEE write enable to 1. So these are the steps in order to write data to the EEPROM. Okay, then let's see an example. So the read, write an AVR program to read the content of EEPROM location hex 005F and write it to port B. Okay, so let's start with the dot include. Make sure that we always write that. 128 def dot inc and LDI R16 0 hex FF. Now I want to make port B to be an output port. That's why I'm doing this. Out DDRB R16. So port B as an output port. Then, now step was there. If I go back, I have to wait write enable becomes 0. So the instruction over there that I can use is check to see the last write is done. I can use skip bit if cleared instruction. And which one I'm checking? From the EECCR register, I have to check EE write enable. So from the control register, I have to check EE write enable bit, which is this one. And I have to skip the next instruction if this is cleared. So I can say check EWE to see if last write done. And then if not, I have to wait until it's done. So wait should be here. Now, if it is set, then I have to skip the wait and I have to set for the next instruction LDI R18 0. So we can say load high byte of address to R18, and that high byte is going to be out EARH R18 high byte to EARH. Then the low byte LDI R17. If you can use the same R18 because we already set EARH, and we can set that to the value for that was 5F. So we set the 0 and the low byte is 5F. So load low byte of address to R18, out EEARL, R18, low byte to EEARL. So we have done that. We know the address, and we just need to read now. So in order to read that, I can just set bits for it, SPI, EECR, and which bit, EER, E bit, it has to be set in order to, so set read enable to 1. Now we are ready to read, and then I have to check an R16 and the data register of the EEPROM. So it will be copied over there, load EEPROM data register to R16. And then I have to send this data to port B, R16 port B. I can say out R16 to port B. That's it. So this is how we can read data from an EEPROM. And the write steps are also already covered over there. And we have to check again. We have to put the address that we want to write, and then write the data into the EEDR register, then set master write, and within 4 clock cycles, we have to set the write enable. So let's do an example related to that as well. Write an AVR program to store G into EEPROM location hex 5. So again, we have to use the include file, and we have to check for the last write. So I can use this instruction over here. Oops. So check for the last write, and then if not, wait, like we have done it in the previous one. Then we have to load the address, so we can use this again. It's the same address, so I can just copy and paste it over here, low byte and high byte. Now I have to load letter G, so LDI R16 letter G, ASCII G. And then I have to send this to EEDR register. So load R16 to EEPROM data register. And then SPI. So from the control register, I have to set master write enable. And then I have to set EEPROM write enable. So set write enable to 1, and that's it. And this has to be done within 4 clock cycles. That's how we do the write with the EEPROM. If you want, there's a code example in the books, binary to ASCII conversion. So it's useful whenever any data needs to be displayed using ASCII characters, LCD or PC screen, and all AVR products use little endian conversion, high digits to the higher address and low digits to the lower addresses. And you can write a routine or a program which calls when ASCII to convert subroutine to read a byte from a port A and convert it to ASCII digits and save to the data memory starting at next row, hex 210. Now, we can go through this quickly. I'm not going to go into the details of it, but at least you can see what's going on. So if we talk about what we need to do first, as we are going to use a subroutine, we have to initialize the stack. Then we have to call this bin to ASCII convert function or subroutine. And we have to read the number from port A, set the denominator to 10, and divide and convert remainder to ASCII and store it. So we just need to do a conversion and set numerator equals to the quotient and divide, convert remainder and quotient to ASCII and store it. So this is like a mathematical formula that we need to apply. And label the registers and the memory addresses to be used for code readability. Initialize the stack. If you want, you can use a macro. Make port A an input port and call bin to ASCII convert. Since the algorithm uses division 5 times, define a subroutine for this. So you can also define a subroutine for the divide as well, like we have done it in the introduction chapters. So here is the code for it. The numerator, denominator are defined for the registers, R20, R21, quotient R22, and ASCII result will be written to hex 210 as it was given in the question over here. So these are all defined. Now in the main program, we have to initialize the stack. The macro is written for initializing the stack. You can use it like this. So A has to be set as an input. That's also done. And then we have to call bin to ASCII convert subroutine. That's all you need to do in the main program. And there's a divide subroutine, which you need to do a division. The quotient is given. You have to set the quotient to 0 and then increment it. You have to do a subtract operation as we don't have a divide in AVR. So you have to subtract the denominator from the numerator. Check for the carry. If not, we have to redo that. Otherwise, decrement the quotient and add denominator to the num and then finish it. So bin to ASCII convert. We have to initialize the pointer for the register X for the ASCII results that we want to write to. Then get the value or the number from the pin A. And then we have to set the denominator value to be 10. We call the divide function over here with the relative call. And then once this function is completed, it returns back ORs with x30 because we want to create an ASCII digit. We have to OR it with 3 so that 3, 0 or 3, 5 is going to be actually 5 as a number. Then save the lower digit, copy the quotient, divide again, and then OR it again, and then save the next digit. And it goes like that. And then final quotient to be an ASCII digit, and we have to save the last quotient, which is going to be the last digit. You can try this by yourself. You can find more details also in the book about this. Now, the last thing that I want to consider is the checksum. Now, the checksum in typical applications, it detects if there's a data corruption. So we have to understand how we can do a checksum operations or checksum arithmetic, let's say, and we have to know how to calculate it. We have to add the bytes together and drop the carries and taking the 2's complement of the total sum in order to calculate the checksum byte. And in order to test the checksum, add the bytes together and drop the carries add the checksum byte to the sum, and if the result is not 0, that means data is corrupted. So let's see an example. Find the checksum byte for the following: 25, 62, 3F, 52. Now, when we add them together, 5 plus 2, 7, 15, 7, 22, 24, 24 minus 16 is 8, so 8 is written. We have got a carry. 6, 3, 9, 12, and 17. And 17 minus 16 is going to be 1, so 1, 8. X18 is the output of it. Now, we can write 0, 0, 0, 1, 1, 0, 0, 0. When we take the 2's complement of it, this becomes 0, 0, 1, 0, 1, 1, 1, which becomes E8. Now, this is our checksum byte that we have got. In order to test that checksum byte, I have to add all together 25, 62, 3F, 52, E8. When you sum them up, this is going to be 24 plus 8, 32, minus 16. It's going to be 16. So this is going to be 0. And then the second part is we have got a carry over there. So we have to add 17 plus 14, 31. 31 minus 16, it's going to be 15, which is 0 as well. So this is how we can get 0, and this confirms that the data is not corrupted, because if it's not 0, it means the data is corrupted. So this is how we can do the checksum calculation. And you can also find a subroutine so that you can create a checksum subroutine, and you can use it in your programs in order to check if you have right data stored in the EEPROM. That's all I want to say for this chapter. Thank you for listening.